Okay, hello again. In this video I am going to show you how to derive an expression for the electric potential for a uniformly charged disk. So let's start off with a picture of the disk. I'm going to draw a disk here from the side view. The radius of the disk is going to be r. Okay, and we're going to put a charge plus q on this disk. Okay. We're going to spread it out. So you could draw some pluses on here. But the idea would be that we're spreading out the charge evenly. Okay? So in our derivation, we're going to talk about a value of sigma, right, which would be something in coulombs per square meter. And we're going to assume that that sigma is constant. Okay? So this is going to be a uniform distribution, and that means that sigma is the same everywhere. And so that's important. So this disk is probably an insulator. It's a plastic or something like that. If it was a conductor, the charge wouldn't spread out evenly. The conductor would go to the edges of the disk. But we're talking clearly about an insulator here. Okay. Now, we want to take the disk and we want to find the potential, or the voltage, whichever you prefer. We want to find it a certain distance away from the center of the disk. And we're going to assume that we're on the axis of symmetry of the disk. So that's a big assumption here. Okay? So just like I drew it, when I talk about x, x is the distance from the center of the disk traveling out, perpendicularly to some point P. And that's what we want to get. So we want to find an expression for that. Okay? Alright, so to do that, we want to break this down by calculus somehow, and we want to add up all the contributions of the pieces. Now, the problem is that you can't make a piece like this. You can't make a dq that's just a little chunk, because it would be super difficult to actually add up those chunks in an integral in a way that's easy for us to do. Right? It's just not convenient. When we did the ring of charge, that was convenient because all the chunks were the same distance from the center. But in a disk, that's not true, so we can't do this. So the trick that we're going to use here is we're going to make our dq's come from rings. And so I'm going to define some ring here that has a radius of lowercase r. And what I'm going to do is I'm going to add up all of the potentials that come from rings, and I'm going to let the rings start really small at 0, radius of 0, and they're going to go all the way out to a radius of r, uppercase R. So kind of symbolically, I'm going to be adding up the potentials from the rings. Okay. And in the other example that we did in class, we derived the potential for a ring already. So we're going to use that result in this problem here. Okay. So I'm immediately going to go and I'm going to substitute in the result that we got from before. So for dV, I'm going to write k. I'm going to write dq here, okay, where dq is the charge on a ring, like an individual ring, like the one we drew. So dq would be whatever charge is on here. And then that's divided by r squared plus x squared. And if you forgot where that came from, remember from our other derivation that that is the distance from the ring to this point. So r squared plus x squared. And that's from the Pythagorean theorem. So this is actually the result we got from before. I think we called it a before, and now we're calling it r. And we're going to have to let that r vary from something small, like 0, up to something big, like uppercase R. Okay. All right. Now, what else do we have to deal with here? Well, in this problem, we don't want to keep DQ. Okay, we don't want this because it's going to be changing as we go to bigger rings, and we need to account for that somehow. Also, it's hard to do the integral because we really want to replace this with dr. So we want to substitute. We want to replace it. Because dr can be integrated from 0 to r, and dq cannot. So what I'm going to do is I'm going to make use of the fact that sigma is constant. And I'm going to say that sigma for the total disk would be given by the total charge over the area of the disk. This is the global sigma, right? Meaning for the whole shape. And then I'm going to insist that that's equal to the local sigma. And what I mean by that, the local sigma is the density of charge spread out around the ring. So now I'm going to talk about dq. And the clever way of doing this is, how do you express the area of a ring? Remember, we talked about this with like a roll of tape. How would I get the area of this dark part of the roll, right, the side of the tape? I'd have to stretch this out to a circumference of 2 pi r, and then I'd take the thickness of that. So the trick would be to do this. Okay. So I'm going to open up this little ring, stretch it out into a line. It's equal to the circumference, and I multiply by the thickness. So the thickness would be that. I know it's super thin in that picture, but it's the thickness of the line. And so by making these two densities the same, I can now do my substitution. Okay, so I'll put that down here. It looks like the pi's cancel out, and I'll end up with dq equals, what do I have? I've got 2q r dr divided by r squared, where that's the radius of the disk. And then that's going to help me out. So that was a pretty important step right there to do what we did. That's going to allow us to get rid of dq in the integral and replace it with dr. So I'm going to do that now. And so I'll have k times 2qr dr divided by r squared times that part, which is the distance part. Okay, you can check the math there. Now I've made this into an integral with dr, and so I can go and say that that's going to run from 0 to r. So r is the variable of integration here, lowercase r. Okay. Uppercase r is the radius of the disk. It's just a fixed value. And this little r squared plus x squared, remember, that's this distance here, which is changing. Okay? So because that distance is changing with r, we cannot take it out of the integral. So I'm going to take everything out that I can. 2kq. I can also take out the big R squared because that's the radius of the disk here. Okay. And then I'm left with r dr all over this. And that's how you set up this integral. Okay. So please, please, please pay attention to the differences between the three variables here that involve length. You have x, which is essentially a constant for the integral. You have lowercase r, which is the variable of the integral. That's not a constant. And then you have uppercase r, which is the radius of the disk, which is a constant. So that we could take this out, but the other things had to stay inside. Alright, I'm going to stop the video here, and then the next part of the video will simply be doing the calculus on this to get the solution. But this was the important physics on this slide.